In this screencast, we take a few minutes to take a look at some very basic set theory, the kind of set theory that would be relevant to very young people, and the kind of set theory that you are probably familiar with because you have probably seen this diagram before. All diagrams of circles of this type are called Venn diagrams. Sometimes they are called Euler diagrams, but I've not heard that term. But your text says they're called Euler diagrams. So there's a set A and a set B, and there are some things that are in A but not B, and there are some things that are in B but not A, and there are some things that are in both A and B, and there are some things that are outside of both A and B. This is the familiar setup of a Venn diagram. Sometimes the Venn diagram looks like this. In this case, we say that A is a subset of B. We write that A is a subset of B. This means that anytime there's something in A, that something is also in B. It is not necessarily true that all of the things in B are in A, but it is true that all of the things in A are in B. So if these are the even numbers, these might be the integers generally. If these are the perfect squares, these might be the whole numbers. Sometimes the Venn diagram looks like this. In this case, we say that A and B are mutually exclusive events. What does that mean? That means if something is in A, it cannot be in B. If something is in B, it cannot be in A. There is no intersection between the two. A little bit of vocabulary. This is called the intersection of A and B. This part is called the intersection of A and B. This is red, A intersect B. You're like, that's purple. I'm saying that the way that we would read this is to say A intersect B. Now, the whole Venn diagram, the whole Venn diagram, the whole Venn diagram is what we call a union B. So all of this is a union B. This is all of the stuff that's in A or B or both. In this case, A union B is just the two circles. Okay, so that's just some vocabulary. So we imagine if you had the set of all dogs and the set of all pets, what would the Venn diagram look like? Well, I would think that the Venn diagram would look something like this. Because lots of dogs are pets. But there are some dogs that are not pets, and there are some pets that are not dogs. Now, there's not that many dogs that aren't pets. Most dogs are pets. But still, there is something out here, so we make the Venn diagram like so. Let's see. Oh, that's too thick. Let's take the set of perfect squares and the set of whole numbers. What does that look like? What does that Venn diagram look like? Perfect squares are numbers like 1 and 4 and 9 and so on. And the whole numbers are numbers like 0, 1, 2, 3 and so on. So the set of perfect squares sits inside of the set of whole numbers. Because 1 is in here and also a whole number, but 5 is not a perfect square, even though it is a whole number. I'll give you one other mathy one to think about. Isosceles triangles and right triangles. Well, that's this, I think. Because you could have an isosceles right triangle, but you could have a right triangle that is not isosceles, and you could have an isosceles triangle that isn't right. Okay, so let's take a look at whether or not arguments are valid, and we'll take a look at that through the lens of the Venn diagram. If you were to think about horses and dogs and four-legged animals, would this argument be valid to you? A horse has 4 legs, that's true. A dog has 4 legs, that's true. Therefore, a horse is a dog. Is that true? No, not necessarily. Uh, you have the set of 4-legged animals. This is the set of 4-legged animals. Dogs and horses are in that set, but they're not necessarily the same thing. And so this is what we would say not valid. It is not true that just because this is true and this is true, that this has to be true. Similarly, all squares are rhombi. Rhombuses is not a word, rhombi. All rhombi are parallelograms. Therefore, all squares are parallelograms. This is a true statement. This is a true statement. If this must be a true statement, then we say that the entire argument is valid. If this doesn't have to be a true statement, even though those are, then we say that the argument is not valid. Well, by the fundamental law of textbook examples, this has to be valid, right? Because that one was not valid. But why? All squares are rhombi. So if this is the set of all squares, this is the set of all rhombi. Everything that's a square is automatically a rhombus. And then all rhombi are parallelograms. So if this is the set of rhombi, then this is the set of parallelograms. Everything that's in the set of rhombi has to automatically be in the set of parallelograms. Where does that put the set of squares? Puts the set of squares within the set of parallelograms. This must be true. And so the argument is valid. If the first 2 statements are true, then the last one must follow. So we can use Venn diagrams to help us establish that arguments are valid or invalid. Hopefully this is helpful to you. I look forward to seeing you when we gather.